This is OPTI 380A, Lab 11, Detectors. I'm Sedona Zeller.
I'm Sophia Centeno.
And I'm Ethan Luker.
And our TA is Abar Liaf. In Part A of Lab 11, we compare the responses of a PIN photodiode, an APD, and a photoconductor to the same LED source. They all convert light into an electrical signal, but in different ways, and the 4 procedures demonstrate those differences. We used the LED board, function generator, PD amplifier, oscilloscope, multimeter, APD, pin diodes, CDS photoconductor, strobe setup, and a black cloth to block room light. We began by aligning the APD and reference pin diode with the LED, covering the setup and adjusting the LED amplitude until both signals were visible. Then, we switched to the second pin diode to record open circuit voltage and short circuit current versus optical power. After that, we replaced the pin diode with the photoconductor and measured how its output voltage changed as we adjusted the LED. Finally, we measured the pin diode's temporal response with and without the 47 ohm load resistor to see how the fall time changed.
For the APD versus PIN photodiode comparison, we saw that the APD had a much clearer signal, while the PIN photodiode signal had a lot of noise. From the optical power measurements, the open circuit voltage of the PIN photodiode increased steadily with light level. The VOC curve was somewhat quadratic and began to flatten at the dimmer settings. The short circuit current increased linearly across the full range with a slope that matched the diode's responsivity. When comparing these graphs to the typical thin photodiode behavior, they seemed normal. For the photoconductor, the measured voltage rose slightly with light intensity but followed a non-linear trend. It responded more strongly at low light levels and began to saturate at higher intensities because the device resistance decreased toward the limit set by the series resistor. Lastly, the temporal measurements showed that the PIN photodiode had significantly longer fall time with high impedance, while adding the 47 ohm load produced a much faster decay, demonstrating the impact of RC time constant on the detector bandwidth. Overall, Part A demonstrated the high sensitivity of APD, the linear electrical behavior of the PIN photodiode, the nonlinear response of the photoconductor, and the effective termination resistance on detector speed.
Part B. We looked at CMOS spectral imaging using a Thorlabs camera. The goal was to understand how different wavelengths, both visible and infrared, are detected and how an IR blocking filter affects the image the camera captures. We mounted up the CMOS camera with a lens on an optical rail and imaged a resolution target. We first used white light illumination and then inserted an IR filter. Next, we turned off the lights, used an IR LED for illumination, and repeated the process with and without the IR filter. We captured images of the resolution target under ambient white light. The brightness slightly dropped when the IR filter was added, which showed IR light wasn't significantly blocked. With the IR LED and lights off, we captured another image. This image nearly disappeared when the IR filter was added, which proved that the filter effectively blocks IR wavelengths. In Part A, we compared the PIN photodiode, photoconductor, and avalanche photodiode. We saw how each responds differently to light intensity, with the APD being most sensitive and the PIN showing a linear response. In Part B, the CMOS camera detected both visible and infrared light, and the IR blocking filter removed the infrared portion. Both of these results showed us how detector design and filtering control a system's overall spectral sensitivity.